Alright, so we have a function which is continuous, and we want to show that this integral on the left is equal to... what's that on the right? Well, it looks like in this PDF file, this integral was cut off. So, this is the... and this, I remember this sometimes happening in, I think one of my classes I had a professor where this would happen sometimes. But basically, what part of this exercise is that we have to come up with a the first part of the problem is determining what the problem statement is. And I think I had a professor once who every once in a while I don't think I think I was sitting in on the class and I didn't sit in on it for very long, but it was like sometimes the exercises would be like really interesting problems, but it was phrased in a slightly incorrect way that made it trivial. And so the first thing you had to figure out was, what is the question really asking for? And then the next part is to actually solve the intended question. So what should this integral on the left be equal to? Well, with me being more visual, I like to sort of draw this out. So let's see here. We've got this. This is A, this is B, this is B. So we've got our x values and our y values, because we're integrating from AB to AB. So on the left hand, we're integrating. So y is, so we got this and we got this. So y is ranging from A to B. And then for each y value, we integrate f from x equals A to y. So if we fix a y value, then we start at A. The x value starts at A and it goes out to y. So if we draw a dashed line here, which is f equals y, so we would go, or x equals y, it would go out to here. And so then if we're considering this region from y equals A to B, this region that we're integrating over looks like this. So, it says to compute the integral of c in two different ways for a suitable set of c, and of course this is going to be our set c. So we know that this is what it looks like when you first range over y and then range over x. So what if you range over x and then range over y? Well, certainly x can range over any values between a and b. So the x integral should start at a and go up to b. And then for any fixed x value, if you look at what the y will be, well, you first start at this line y equals x. So you would start at x, which is what we have in the lower bound, and then you would go all the way up to b. So it should look like this. And that is the correct problem statement. And now we are done with starting the problem. So now we start the problem. All right, so I'm going to let c equal the set of all points x comma y, where so x is between a and b, and then for any fixed x, y is between. No, I want to do this backwards because I want to make this agree with the left hand integral first. So left hand integral, y ranges from a to b, and for any fixed y, x ranges from a to y. So we can write it like this. And then if we want to write it in terms of what it looks like on the right-hand side, this is all x, y, such that, so we first let x range from a to b, so x is between a and b, and then for any given x, y ranges from x to b, so x is less than or equal to y, which is less than or equal to b. So this is what our set C is. We want to compute the integral of c, the integral over c of f. And what that really means is we're integrating the function chi c, indicator function of c, times f. All right, so the mu of the bound the boundary of c has measure 0. Why is that? You can sort of do that by visualization. The bound, so boundary of C, it consists of, well, it's the boundary of this triangle. So you've got this left-hand side where you consider x equals a and y ranges from a to b. So it's going to be x is a. You take this cross with y goes from a to b. And then you've got this other, you got the horizontal line on top of the triangle, which is x ranges from a to b and y is fixed at b. So x can go from a to b and y is fixed at the value b. And then we take the union of this with the set of all points x, y such that x equals y. And of course, x and y are both between a and b. All right, so the boundary of C is this, so the boundary of C is a set of measure 0. And that's because, well, we can take this first set here, and if we've got A cross interval AB, we can cover that by, in X, you cover that by, you'd go A minus epsilon, comma, A plus epsilon, take the cross product of that with A, comma, B. And that would give you, if you make epsilon arbitrarily small, you get an arbitrarily thin box. So you can cover that with a box. You can cover the second one with a box. Similarly, I'll just draw it out. You cover this with a rectangle. You cover this with a rectangle. And then you can also cover x equals y with a rectangle. Do I need to prove this? I don't think so. Basically, what you can do is you can break up the domain into a number of like sub-intervals here. And for each of those sub-intervals, you get a box. And these boxes will cover here. So let's say let's just prove this. The measure of this set is 0 because let's call this C1. The measure of C1 equals 0. Let's call it E. I want to give it its own letter. The E is a set of measure 0 because for any n, E is covered by n rectangles of the form, and then you'd go, let's see here, it'd be like I over n, I plus 1 over n, cross I over n, I plus 1 over n. That's what these boxes I've drawn up here look like. So I would range from 0 all the way up to n minus 1. So that's n boxes, and you cover... Oh, wait, but you have to normalize this. Now this gets more difficult. So, here. Well, first of all, what I'm going to do is instead of doing it the cross product of something with itself, I'm just going to call it itself squared. And then what do I need to do to this set? Let's see here. I need it to start at A and go all the way to B. So it'd be like B minus A over 2. So when I plug in I equals 0, I need A. So I need I over n plus A. But then I need it so that when we plug in, so then I plus 1 over n plus A. Now if I were to take this all the way up to I equals n minus 1, then I want B. And here I would get A plus 1. So this I plus 1 over n, when I plug in I equals n minus 1, I get 1. But instead I want B. So I multiply this by B. Right? Yeah, when we plug in I equals 0, we go from A to A plus B over n. Oh, no. This needs to be B minus A. There we go. When we plug in I equals 1, when we plug in I equals 0, the left endpoint is A and the right endpoint is going to be 1 plus 1 over 0 plus 1 over n, so that's n. So B minus A over n plus A. So basically 1 over n times the total length of the interval time plus A. And then when you plug in I equals n minus 1, then the right endpoint is going to be 1 times B minus A plus A. So that's B, the minus A and the plus A cancel, and you get B. So there. So it's covered by n rectangles of this form. And so the total volume of these rectangles is, well, there's n of them. And then if we take the volume of any particular one of these, well, the difference is just B minus A over n. Because what will happen is if you take this I plus 1 over n B minus A plus A and you subtract I over n B minus A plus A, the only thing that will be left over is that the I plus 1 in the right-hand side, you can factor that out and that'll give you B minus A over n, and everything else will cancel. So you get this B minus A over n, and so this is the length of the one interval, but because we're finding the volume of the rectangle, this is the length of both the base and the height, so we have to square it. So the total volume, we've got n of these rectangles, and each rectangle has area B minus A over n squared. And so this is going to be equal to B minus A squared over n. Which goes to 0 as n goes to infinity. Meaning that given any epsilon greater than 0, you can give an n large enough so that B minus A squared over n is less than epsilon. Meaning that the corresponding rectangles have total length less than epsilon, but cover this set E. And so therefore E has measure 0. Okay, that took longer than I was expecting it to. And you might not need to go through all that detail depending on how much detail your professor wants to see, or whoever's teaching this course, or if you're teaching it to yourself. But that's how you'd go about proving this part rigorously, but you can just see the fact that this is like a line embedded in two-dimensional space. That means that it's going to have measure 0, basically. But yeah, so anyways, the point is the boundary of C has measure 0. I'll put this all in parentheses, because that sort of supports the fact that the boundary of C has measure 0. Okay. This means that the indicator function well, let's see here. This function is discontinuous on a set of measure 0, namely the boundary of C. And since f is continuous everywhere because it's a continuous function, the indicator function times C of C times f is discontinuous everywhere. No, what am I talking about? Continuous everywhere. So this is discontinuous on a set of measure 0. All right, and we know that so this product of two functions is discontinuous only on a set of measure 0. And so basically this product is going to be integrable. So we want to jump to that, but there's something that you need to remember, and that is that you need these functions to be bounded. That's important. Chi C is, so I'm just going to come out and say it, these Chi C and F are bounded. So chi C is obviously bounded because it only takes on the values 1 and 0. F is bounded because F is a function and its domain is a compact set. And it's a continuous function. And basically the image of a compact set through a continuous function is itself a compact set. That is a theorem from way back in the textbook. So if you have a continuous function and you plug in a compact set, you'll get a compact set. So the domain of F is compact, so its range is compact. And compact as a subset of R means closed and bounded. So it's closed. Now, bounded, that's the one we want. What am I talking about? Okay. So the indicator function C and F are both bounded. So the product is. And so, because these are bounded functions, chi C times F is integrable. Because the fact that having a set of discontinuities of measure 0 is equivalent to integrability is only true for bounded functions. Now, I do also think maybe it would have been, I think we have an exercise that says that products of integrable functions are integrable. I think that it might have been easier actually to do that because chi C is obviously integrable. F is integrable because it's continuous everywhere and it's bounded. Well, I guess it uses the same exact facts that we've used here. So, yeah, there we go. However you want to phrase it. We get that this function, chi C times F, is integrable. Because it is bounded and it is discontinuous only on a set of measure 0. Alright, so now we get into the calculations. So what we're going to want to do is, like it says, we're going to want to compute the integral of C times F. And we want to compute it in two different ways. And obviously the integral of C times the integral of F over C, I guess you would say. The integral of F over C is basically the integral of the function F times the indicator function of C. And it says to compute it in two different ways. Well, we have Fubini's theorem, and that tells you two different ways of computing an integral. You can compute it in terms of x then y, or you can compute it in terms of y then x, and that's exactly what we're looking for in the problem statement. Is we want these two different integrals to be equal. So that sort of should give you a hint as to how we should move forward with that. So now we want to set up this integral. So let's see here. What is the best way of doing this? So let's see here. If we take this function g, I don't know if this is absolutely necessary, but I like writing this out just to be very detail oriented and clear on what I'm doing. So if you fix an x, let gxy, so this is basically going to be chi c times f evaluated at xy, where x is fixed. So it's going to be a function only of y. So it's going to be, so if x is fixed, then we have this indicator function. Let's remember how this function c works. If x is fixed, then in order to be in c, y needs to be between x and b. So the indicator function on this interval from x to b of y, this is times f of xy, and g fix y and plug in x, the indicator function, well, if we have a fixed y, then x will range between a and y. So interval from a to y, x, f of xy. Then, if we look at this integral, let's see here, which one do I want to do first? We want to do dx dy first. Okay, cool. So, let's do this. The integral over c of f, so we're going to integrate from y equals a to b, and then from x equals a to b, chi c f dx dy. So what this means is that we're doing this integral from a to b, So now when we're integrating dx, that means we have a fixed y. So we're doing gy of x. So this is going to be chi ay. Well, I guess let's just do it this way. Let's just write out this extra step. F dx dy. So this is going to be integral from a to b, of indicator function ay x, then we've got f dx dy. And so then this indicator function, because we're integrating x from a to b and the indicator function is a to y, well, that's all that's going to matter. So we just have the indicator from a to y, f dx dy. So that's one of the things that we wanted. And then the next thing, if we compute it the other way, if we do the same integral, but we do it dy dx. And by the way, this is all doable because of Fubini's theorem. By Fubini, because f is integrable. So this is going to be, again, it's going to be integral a to b. This time it's going to be gxy f dy dx. So I'll skip the next step where I just plug in the chi function, and I'll just put it straight into the integrand, because that's how it works. So this chi function, this indicator function, it goes from x to b. So x to b, and then we've got f, because the indicator function is built into the bounds of the integral, dy dx. Hence, a to b, f dx dy is going to be equal to integral a to b, integral x to b, no, what am I doing? This is a to y, then a to b, x to b, f dy dx. And so there you go. That is how you do this problem. And this is sort of like a standard, I feel like this is one way to get like interesting things out of Fubini's theorem, is that you take a function and you integrate it in two different ways, and you find that those two things are equal to each other. For this particular example, I don't know if knowing that these two things are equal to each other is particularly useful or interesting. It's just, I think, more practice in using Fubini's theorem. But the more interesting thing is, like, if you imagine, what if there's a scenario where you're given this formula, this integral formula on the left-hand side, and you don't know how to compute it, but you know how to compute the integral on the right-hand side, and so you use Fubini's theorem to find an integral of a function f, which will equate these two things. I feel like that's a more interesting example of this. And yeah, I think that's just more of like a general mathematical concept of, like, you have a formula that says that these two, or you have a theorem that says that these two formulas are equal, and then you come up with some formula in your research and you want to figure out how can I evaluate this formula, but you make it look like something that you would get out of a theorem like this, so that you can equate it to something else that's easier to evaluate. But anyways, examples like that, maybe there'll be more interesting examples like that in the following exercises. But for now, this is all we have to deal with for this problem, and so we are done.